So we finished example 6.8 in the fatigue chapter, and we are going to 6.9. Let's see if we have enough time to go through this problem. If it is a simple problem, I will just breeze through that and we will go to the next slides. 6.9, this is the problem. Yes. So in this figure, it shows a rotating shaft simply supported in the ball bearings. Okay, so you have two ball bearings supporting the shaft here, and the shaft is rotating. I think this is the point A and D over here, and it is loaded by a non-rotating force F of 6.8 kilonewtons. Using ASTM minimum strengths, estimate the life of the part. Okay, so if you look at this problem, what kind of a problem is this? First, if you recall, we had derived some equations to estimate what would be the life of steel specimens. What is the formula? We have to recall, since it has been a few classes. If you recall, this is the formula to be used, where A and B we need to find after we find the fatigue fraction F. From one of the graphs are different formulas to find F value, and then we apply this formula to find the life of the specimen. So we need to find what is the sigma reversible load in our case, and then find A and B and just apply the formula and figure it out. Okay, so let's go back to that problem here. So here, what is the load we have? We have the 6.8 kilonewton load. Remember that the shaft is rotating. When the shaft is rotating, but the load is static, what will happen? A point, any point you choose on the shaft, at one time, if it is under compression here, this point will rotate and go to the bottom at a different time. The same point will come to the bottom and will be under tensile load. So it is alternatively under compressive and tensile load, and the stresses are going to be equal, assuming this is the centroid is the neutral axis for this particular case. Here we need to first identify the critical point. So when you are solving these kind of problems, you need to find where the stresses could be maximum. Since we have stepped shaft here, here and here, most probably due to stress concentration effects, the stresses are maximum here or here. However, if we take a look at this problem, we are not given any radius as such, the fillet radius. So we cannot actually figure out what is the stress concentration factor, and perhaps they consider this point as the critical point where the bending moment will be maximum. For a simply supported beam, you know how the bending moment diagram is. It will be like this, reaching a maximum value where you apply the load. So we just need to find what is the maximum bending moment load. So I'm not going to fully solve this problem. This is straightforward problem. You can figure out what is the maximum bending moment load by simply multiplying 6.8. Let's see here. So we need to first solve for R1 and R2. After we solve for R1 and R2, then we can find right at this point what is the load. So solve for it, R1 plus R2, write equilibrium equations, take moment about point A, you will get another equation. We know the total distance between A and D. We have 125 plus 100, which is 225, plus 75, which is 300, 400, 550. So we get 550. R2 times 550 must be equal to 6.8 times, we have here this distance 250 plus 75, 350 minus, so 325. So by solving this for R2, and R1, then you can draw the free body diagram and directly figure out what is the load here right at this point. So let's consider this point as E. So right at the point E, the bending moment, internal bending moment, must be equal to R1 times the length 325. Okay. So if you find the M max value, once you have the M max value, you can easily figure out what is the stress. The maximum stress, sigma max, can be found by the formula ME over I times C. Substitute and figure out the sigma max value. The sigma min value will be negative of this value. Okay, and then we can find the amplitude sigma A. Will be equal to sigma max. Finally, you will get, since it is a completely reversed load, sigma A should be equal to sigma max. Once you have that value, then you need to figure out for the given material what is a C prime. Again, we use the empirical formula. Once you know the SUT value from the tables, you can utilize the SUT values to calculate a C prime as 0.5 times 690. Then we have to also figure out what are the 6 Marin factors and find SC value. Okay. So once you have these values, again, they are also figuring out what is KF. Not sure if they have given the R over D ratio in the figure. I really do not find the R value. Somehow they have taken the R value as well. Let's see here. R is taken to be 3 mm, and then they have evaluated what is the KT value from Peterson's graph. Once you have the KT value, then they have evaluated KF, which is the fatigue stress concentration factor, using the formulas, and then they found the sigma max value by this formula. Okay, so once you have the sigma reversible, find A and B, and then you can easily figure out what is N. Again, so the procedure is same. The procedure is same as the example 6.8. We go through the same procedure to figure out all the values and then find the number of cycles to failure. Okay, so you can look at the previous lecture and try to see how to do all these calculations. So let's go to a different topic now. Now we are going to see cases where we do not do completely reverse loading. What is a completely reverse loading? If you remember, any load like this, where sigma mean value is equal to 0 and the sigma amplitude is equal to sigma max value. This is the sigma max here, is completely reversed loading. This is a completely reversed loading. Now consider a case where we do not have the completely reversed loading. So this is the 0 point. So instead of having completely reversed loading, if you apply a load like this, then how do we calculate N? Okay, so what is the formula for N? N we have seen, the formula is sigma reversible. Remember, the stress here is sigma reversible. Okay, over, we have A raised to the power 1 over. So unless we find a sigma reversible, an equivalent value of sigma reversible for this case where we do not have a completely reversed load but a positive mean stress value greater than 0, in that case we need to find an equivalent sigma reversible load If we can find the equivalent reversible load, then we will be able to figure out what is the number of cycles to failure for this case. Okay, so we are going to go through some theories which will let us know how to calculate the equivalent sigma reversible load. So let's go through this point. The SN diagram is applicable only for completely reversed stresses. Other fluctuating stresses exist. Sinusoidal loading patterns are common but not necessary. So this is a sinusoidal wave loading pattern. We may have random fluctuating loads as well. So let's see some of the loads. So this is a random fluctuating load. In fact, if you see any vibration problem, it will be much more random. You take a typical vibration problem. The vibrating loads will be random like this. So how do we how do we solve for such problems? Before going to the complicated problem like this, first we need to solve for sinusoidal patterns with the non-zero mean stress value. We have several cases given here. So this is a completely reversed load which we have solved. This is a constant frequency load with a positive mean stress. Again, this is also with a constant frequency, positive mean stress. Now, if you take this particular load, it is completely random. The frequency may be different. So between this and this sinusoidal pattern, we can see the frequency is different and it is very random load. Again, we can see here we have a sinusoidal pattern here with the same amplitude of stress. However, the frequency is varying. As we go in the time, we can see the wave gets shorter and shorter. Okay, so there are different cases which are possible. Another case where we have, although in a global level, we can say this is a global level, although we have a maximum and minimum value. When you zoom in here, you will see much variation in the stress. The stress is not constant. If you zoom in, that itself is like a sinusoidal pattern. If you zoom in into this area, you will see variation in the stresses. So when you have conditions like this, especially in vibration, this is possible, then how to deal with it. So before we go to again complex patterns, we will first look for a pattern like this or this, where we have here the minimum stress is 0, over here the minimum stress is also non-zero. Okay, so first let's define what is the amplitude and mean stress. The amplitude is always positive. Okay, so what does it mean? What is the amplitude? From the mean stress value to the maximum value, whatever is the difference, that difference is called as the amplitude. This amplitude will always be positive, whether your loading pattern is on the negative axis here, bottom here, or on the top. In both the cases, it has to be positive, and therefore we put with an absolute sign. The amplitude of stress is always positive. Mean stress, on the other hand, can be positive or negative, and it is without the absolute sign. Okay, so we define these two. There is also a stress ratio, which is given by, say, ratio of sigma minimum to sigma maximum, and an amplitude ratio, which is given by the amplitude over mean stress. So all these values can be plotted in a graph, and an output can be given in terms of these 4 different values. Okay. How do we use the fatigue concentration factor, capital KF? In the case of fluctuating loads, how do we use? Do we apply it to amplitude of stress, or do we apply to mean stress, or do we apply to both the cases? So there is a method which is called as the Dowling method, which is suggested by the person who introduced his theory. For the mean stress value, we will take the fatigue stress concentration factor equal to Kf under the condition here when Kf times sigma max value is less than yield stress. So there are three different conditions. If it is greater than yield stress, then the fatigue stress factor for mean stress is equal to this. And if it is greater than 2 times the yield stress value, in that case, we will take it as 0. Okay. What about the amplitude of stress? In the case of amplitude of stress, okay, we will always use the Kf value given here. So when the localized strain does occur, some method recommend only applying Kf to alternating stress and do not apply any Kf to the mean stress. So that is what is meant here, especially when localized strain occurs. Okay, for fluctuating loads at points with stress concentration, the best approach is to design to avoid all localized plastic strain. So if you want to avoid any localized plastic strain, in that case, use Kf for both amplitude of stress and the mean stress. Okay, so either we can go with this approach or we can go with this particular approach. So either way it is okay. Okay. There are three methods, we can say three methods through which we can deal with fluctuating methods. So what do we do here in the three methods? We vary the sigma m value, sigma a value, and try to measure what would be the fatigue resistance under fluctuating loads. So how do we do that? So let's see some examples. In modified Goodman method, what we do is we have a plot of, again, mean stress and the amplitude of stress, just as we said before. And here we have a plot of failure envelope. You can think of it like the failure envelope for the static failure case. So what do we have here? The failure envelope is obtained by joining the endurance strength on the y-axis, here, with the ultimate tensile strength point here. So both on y-axis and x-axis, we join a line from SE in the positive axis and SE in the negative axis straight to this intersecting point over here, and we can generally say that failure doesn't take place if we are within this limit. Fatigue failure takes place if we are outside this limit. However, this has to be modified, hence the word modified here. Modified with what? The yield point. If we cross the yield point, there will be static failure anyway. So we should be also within the yield point in this case. Hence it is modified. The failure envelope is modified with this particular yield point. Now we can join the draw a horizontal line and vertical line and take this as the failure point. However, it is also further modified by drawing a vertical over right at this point and taking this as the failure envelope. Okay. So we generally do not follow this method. So the line over here will be taken as the maximum stress and minimum stress here, and we have the mean stress right in the middle. There is also a master fatigue diagram. In most of the industries, we will have master fatigue diagram, and we will try to follow this. Okay, a simplified version of the fatigue diagram given here. So what does the master fatigue diagram have? You have the minimum stress on the x-axis, the maximum stress on the y-axis. At 45-degree angles, you have the mean stress and the amplitude of stress. Now this particular graph is slightly complicated because there are too many values being plotted. On the y-axis, you don't not only have the maximum stress, you can also see the amplitude ratio and the stress ratio here. Here we have defined the R value, if you remember, stress ratio and the amplitude ratio. These two ratios are also given here on the y-axis as well as on the x-axis. Okay. So let's try to understand this particular diagram here. Where is the failure envelope? Okay. You can see 1 million cycles over here. A line showing if you select any point on this 1 million cycle line here or here, anywhere on this particular line, the component will have a life of 1 million cycles. So you can choose any combination of sigma A, sigma m values, or sigma minimum and maximum values, and choosing any point will tell you what is the life in the specimen. So this is, you can consider 10 power 6 cycles as the failure envelope. If we are within this failure envelope, you will have infinite life for steel specimens. If it is aluminum, we will not have infinite life, still we will have finite life. In the case of steel, we will have infinite life. If we are outside 1 million cycle line, we will have finite life. So outside you may have several lines here giving constant lifelines. So these are constant lifelines. That gives you an idea what will be the life of the specimen. Okay. You also see these lines which are radially projecting in different directions. These lines can be considered as load lines. We will see exactly what is a load line. Just like the case of static failure case, we also have load lines. So this is, again, this diagram is a little bit complicated. Let's take a simpler version of this diagram, which is called as the Hague diagram, and this is what we will be dealing with. Okay, in most of the cases where we have positive or negative mean stress, this is the case we are going to deal with, and this is called Hague diagram. Okay. Okay, so what is a Hague diagram? A simplified version of this. We get rid of the x-axis given here, the y-axis given here. So we only have the mean stress axis and the amplitude of stress axis. Okay. So we have on the x-axis mean stress, on the y-axis amplitude of stress. So now it looks a lot simpler, this diagram. Now, where is my failure envelope? Just like the static failure case, where does my failure envelope lie? So in the case of Goodman equations or Goodman theory or modified Goodman theory, the failure envelope is given by this blue line here. So this gives me the failure envelope. Okay, so let's try to understand this graph. On the x-axis, you have mean stress. Suppose if I am loading along the x-axis, what does it mean? It means my amplitude of stress here is equal to 0 value. So if I am on x-axis, this means it is equivalent to static loading, just like static loading or quasi-static loading. What is a quasi-static loading? Your tensile test. Okay. So if I'm right on x-axis, this is equivalent to having my tensile test. Where will the failure occur in tensile test for ductile materials? At yield point. And fracture will occur at ultimate tensile strength. So these 2 points on the x-axis are important. Now let's do the opposite thing. I'm going to put my mean stress, force it to 0 value, and then I'm going to increase the amplitude of load. So in this case, or if I am right on the y-axis, what does it mean? The y-axis represents a completely reverse loading because my mean stress is 0, but my amplitude of stress is increasing. It is always positive. Remember, amplitude of stress is always positive. So which means if I am on the y-axis, this is equivalent to completely reversed loading case. In completely reversed loading, we have already figured out that if you cross the endurance limit SE for steel specimen, in the case of aluminum, this is going to be your endurance strength at 10 power 6 cycles. Okay, mostly 10 power 6 cycles. Then this point SE or SF becomes very important, corresponding to 10 power 6 cycles. If I am below the endurance limit for steel, I will have infinite life. If I am above it, I will have finite life. And if I continue increasing my amplitude of stress, if I reach the yield point, then yielding will take place. So on the y-axis, I can see here fatigue failure will occur first, and then yielding will occur. Okay. Now we need to consider a case in between the quasi-static loading and between the completely reversed loading in our case, where sigma mean stress is not 0. It is non-zero, mostly positive value here. And for the positive value of mean stress, how do I figure out when fatigue failure will occur? So the modified Goodman theory gives you the failure envelope for non-zero mean stress values in this way. So the Goodman equation will consist of an equation of this line, this flat line, joining SE to SUT value over here. This line represents the failure envelope according to Goodman equation. But Goodman equation has to be modified by the yield line or the Langer line as well. And when we draw the yield line, we see that it intersects right at this point. And if we cross this envelope, then yield failure will occur. Anywhere in this triangular region, before fatigue failure occurs, yield failure will occur. And then fatigue failure will occur according to Goodman equation. If we are in this triangular region, that means fatigue failure has occurred and then yield failure will occur. So here in this region, fatigue failure first, yield failure then. In this region, yield failure first and fatigue failure second. So this gives us the failure envelope. If we are within this region for steel specimen, infinite life. If we are outside, failure has occurred and most probably we have finite life. So let us see the equation for Goodman line. How does it look like? Okay. Before I go to this graph, I will just show you the equation. The Goodman equation looks like this. The equation of that line is represented by this equation. Okay, here N is the factor of safety. Okay. Again, we can see that we can express y. This is the y value, sigma amplitude. Y is equal to mx plus c. We can express this equation in that form, and you will see it as an equation of the line. So let's write this equation right over here for this line. Sigma amplitude over SE value plus sigma mean stress value, the x-axis, over SUT value is equal to 1. So this is the equation of this line. But on the right hand side, we saw 1 over n. We can put 1 over n here. If we add an n over here, these points have to be modified. So this point will become SE over n, and SUT will become SUT over n. So appropriately, the points have to be shifted with a factor of safety. Okay. So by using these equations, we will be able to figure out what is the life of the specimen. How to figure out what is the life of the specimen. We are going to see that. So let me draw the Hague diagram for Goodman equation. Again, recall this is called as Hague diagram. For non-zero mean stress values, we use Hague diagram to figure out what is the number of cycles to failure, or whether the component will have infinite life or finite life. We can figure it out through the Hague diagram. And I'm going to show you how to figure that out. So SE here, let's put SE over N here, SUT over N. Okay. Also remember, we had the yield point. Let's call this SY over N, SY over N. Let's put a dotted line joining these two points. Approximately this is the line. Okay, both lines have equations. This has the equation sigma A over SC, sigma M over SUT equal to 1 over N. And in the case of yield line also, there is an equation. Since this is also a line, we must have an equation. Sigma A over SY plus sigma M over SY equal to 1 over N. So these are the equations. Now, let us suppose we have a non-zero mean stress value. In our particular case, I'm going to use a red point to identify our point. Maybe our component has a stress value sigma A given by this point. So let's draw here horizontal and vertical lines denoting our stress point sigma M and sigma A. So these are the stress values for our component. Now, it's not easy to figure out whether this point, we would have calculated these points, right? We do not know whether the point is outside the envelope or inside the envelope. We have no idea whether it is outside or inside. First, we need to figure out whether the point lies outside or inside. Let's assume we know that it is outside. Okay. If it is outside, we need to figure out what is the equivalent completely reversed loading to figure out what is the number of cycles to failure. Again, recall that from the SN diagram or the Wooler diagram, we had the equation for number of cycles to failure. N is equal to sigma reversible over A times 1 over raised to the power 1 over B. We need to find the sigma equivalent sigma reversible value for our case. How do I find out? Okay. So these are the two things we need to do. So first point, is it inside or is the point inside or outside failure envelope? How do I figure it out? Failure envelope. This is luckily very easy to figure out just by finding your factor of safety n. So which we can figure out as sigma A, write the equation, sigma m value here, sigma A over SE. So given any problem, we can estimate SE just like using the procedure before. We find SE prime and then the 6 Marin factors, and then we can figure out what is the endurance limit. SUT value, we can figure it out from tables. Tables will be given to you. Then we can also calculate based upon the load sigma A and sigma m value. So we know all the 4 values. We will be able to evaluate n, factor of safety. If n is greater than 1, then it implies we are inside failure envelope for steel. If it is a steel material, then we can also say it has infinite life. So we don't need to use, in this particular case, we do not need to use this equation to figure out what is the life. Life is infinite. Okay, so the problem is solved right over here. The problem is when n is less than 1. Okay, if it is very near to 1 or equal to 1, then also it is a problem. So we should consider it as finite life in that case. Okay, n should be strictly greater than 1, and it should be significantly greater than 1 as well. Okay, so if it is very near 1 and still positive 1.001, etc., still it is a problem. So generally, we want to make sure that the factor of safety is greater, much greater than 1, at least 1.5. Okay, so in this case, let's say it is less than or equal to 1. So what does it imply? This means inside, outside failure envelope. Okay, failure envelope. So what does this mean? It means again finite life. So if this is the case, then we go to step 2. What will be the step 2? Step 2 is simply figure out what is the find equivalent completely reversed load. Completely reversed load. Okay, so how do I find the equivalent completely reversed load? What I'm going to do is draw a line from SUT. I'm going to draw a straight line which passes through, just like the Goodman line. I ensure that it passes through my point and it intersects the y-axis at some point. Whatever is this intersection point, that is my equivalent completely reversed load for my point of interest. Now, how do I find what is this sigma reversible from the equation? It's very easy. I write my equation again. Okay. For the blue line, instead of writing for this black Goodman line, I write the equation for this blue line. The blue line will have an intersect sigma reversible here. Okay, which means I can write it here. So in this case, I can write it as sigma A, which I already know. Sigma mean value also I already know. But for the blue line, the denominator, instead of putting SE value, I'm just going to put sigma reversible, which is the unknown. Remember that we already know what is the SUT value. which is the denominator here, SUT. And we already know what is the factor of safety we require. If we require a particular factor of safety, then we can use that factor of safety value 1 over n here. Otherwise, we can also take n is equal to 1 and do the calculation to figure out what is reversible. Sigma A, sigma m, SUT, n all are known. The only unknown is sigma reversible value. And we can figure out what is sigma reversible. Sigma reversible is nothing but if you have 1 over n, you can write it in this way. Let's see here. We have to also take the inverse of that. So we need to be careful. Sigma A over 1 over n minus sigma m over SUT. So that's it. So just find the sigma reversible value by this equation for the Goodman equation and substitute back here, find A and B, and you will be able to figure out what is the number of cycles to failure. So next class we will apply this idea to one of the problems and try to solve it. Before we go to the problem, we will also discuss what happens when your mean stress is negative. Here, the mean stress is always positive. The amplitude of stress we have seen it is always positive, so we don't need to go to negative side, but the mean stress can be negative. What happens? So that also we will see next class. Okay, so I'm going to stop right here. And if you have any doubt, you can ask. Otherwise, we will meet again on Tuesday. Do you guys have any doubt?
No, clear, doctor.
Clear. Okay. Okay, so we'll meet again on Tuesday. Remember, on Thursday at 2 to 4, you have test 1. And we will see where we can get the rooms. If any of the, please come to my office 115, and from there we will find any 2 rooms which are available and take the test on Thursday. Okay, Thursday, April 7th. So see you guys, and I will meet you again on Tuesday.